So this is section 5 for day 1, and we're looking at how the derivative is related to the antiderivative. So we want to start looking at those connections between differentiation and anti-differentiation. And so if we look at from section 4.2, the process of finding the original function from the derivative, okay? And we talked about this back, like I said, back in section 4.2. And it's so important it has this name antiderivative. And so we talked about big F being the antiderivative and little f being the derivative in the relationship between these two functions. So the process of finding big F is called antidifferentiation. And so if we have big F and we take the derivative of big F, we end up with little f. So we talked about big F, we talked about little f, and then we just kind of left it at that. We did a few practice problems, we added a C onto the end, and then I kind of said we'll talk more about this a little bit later, and the bottom line is the future is now. So we're going to talk more about this relationship. So let's try this. This is the antiderivative. So find the antiderivative of f of t, and we call that big F. Now I'm going to do a variable change here for reasons that I'll explain in just a little bit. So this is that big F, little f relationship here. Big F is the antiderivative, little f is the derivative. So we would look at this as saying, you know, what is the function, big F, where when we take its derivative, we get this function, little f. And then, you know, of course, we added a C onto the end. That was that constant of integration that we determined, where we could have any number on the end, because when we differentiated, that number would go away. So we were looking at thinking up a function that ends up having that derivative. So let's try this on a few. So what function can you think of, what big F can you find that has a derivative of little f? So let's think of this. Let's have the derivative be 2t. So what function can you think of whose derivative is 2t? Well, if you think about 2t, the function we started with that we would differentiate would look like something squared, so like x squared. And then plus c, right? Because if it was x squared plus 2, then when we take the derivative of this, we'd get 2x, or 2t. So let's try this again. What function can you think of whose derivative is cosine? So what do we have to differentiate to get cosine? And we have to differentiate sine. So the sine would be the antiderivative, and then we would put a plus c on the end. What function can you think of whose derivative is e to the t? So what do we have to differentiate? We have to differentiate e to the x plus c. And like I said, this variable change, don't think too much about it right now. We'll address that in just a second. So now we have this, and this is the derivative. So what function can you think of that has a derivative of t to the 4th plus 3 all under a square root symbol? And really, the answer to this one is we don't know. But we do know there's a plus c on the end. And really, this last function kind of gets at what we're doing today. We don't really need to know this, because what today's focus is going to be is not finding this per se, but taking whatever this is and differentiating it. So for instance, if I took this and differentiated x squared plus c, where we can think of the c as like x squared plus 7, and I took its derivative, it would just be 2x. So what we're going to look for is we're going to look for the connection between 2x and what we started with, 2t. So let's try this for the next function, sine of x plus c. So we can think of this as sine of x plus 18. Take the derivative, we get cosine of x. And let's try it for the next function. We can think of this as e to the x plus 27. And so we take the derivative of that, we end up with e to the x. So if we look at if we kind of compare the derivative of the antiderivative with our starting derivative, we see that It's the same thing, it's just that we've replaced the variable t with the variable x. And so even without knowing the antiderivative here in this last example, I bet you could tell me what the derivative of it is. So if we look at what we started with, what we can see is that we would end up with the antiderivative with the variable x, but when we differentiated this, we'd end up back with the same form, square root of, and instead of the t, it's x to the fourth plus 3. So this is what we're focusing on today. We're focusing on starting with the derivative, integrating it, and then differentiating it. And so just kind of an aside here, this isn't really in the notes, but so we call this the fundamental theorem of calculus part 1. And it's basically saying we know we have this antiderivative big F of x. And we know if we have a definite integral here, but we have one limit that's numeric, then if we have the derivative here and the other limit, which is a variable, then we know where the derivative is in this notation, and we know what the antiderivative is in this notation. But really what I want to do is, if we look down here, is we want to take the derivative of this. So what we're really doing to this expression is we're taking the derivative, we're integrating it, and then we're differentiating it. And those two processes are reversals of one another. So if we start with something, we integrate it, and then we take the derivative, we end up with what we started with. And this is where the variable change comes in. If you notice, one of these bounds is just a generic location, not a numeric. Like a is a number, but x is not. X is some arbitrary location. So since we're using x as the arbitrary ending of this definite integral, kind of like the right side of the shape that's generated when you have a definite integral, then that plays a role in the final expression, but which means we have to use a different variable here in this intermediate step. So the key to doing this is one limit has to be variable, and the other limit has to be numeric, and I'll address the asterisk in just a second. And when that's the case, we can just plop in the variable. So in other words, here's the derivative. This is still the derivative because we did two things to it. We integrated and differentiated, and these two things undid each other. So we end up just plopping this x right here in the expression. And so that's why we kind of call this the plop rule, because we literally just plop in that variable. So this is the beginning of your notes then. So we have to look at this process as two things that undo each other. So if you can kind of think of, like, let's start with the number 7. And if I tell you to add 3, you would get 10. And then if I told you to subtract 3, which would be undoing what you just did, you would be back at 7. So that's exactly what this process is. We start with the derivative, we integrate it, and then we differentiate it, so we end back up with the derivative. And we have this arbitrary ending location that ends up being represented in that function. And so we have to kind of identify this plop rule so that we know when to use it. And the first thing to identify is that, are you taking the derivative of an integral? So this integral is this symbol here, right? And you've seen that all units. So are you taking the derivative of an integral? If that's yes, then we ask ourselves these. Remember the term dummy variable? Okay, is the dummy variable matching the variable used in the limit of integration? And that answer is yes. So we move on. Is the other limit of integration a constant? And again, I'm going to address this asterisk eventually in a few slides. And in this case, yep, that's what the notation says. So if I've met these three conditions, then I can go ahead and plop in my x into my existing function. So notice I have little f here, meaning the derivative, and little f here as the same functions. It's just that there's now an x there where there was a t. So let's try this now with these three problems. So first of all, we have to identify, am I being asked to take the derivative of an integral? And the answer is yes. Do I have a dummy variable that matches the limit variable? And the answer is yes. And I have a limit here that's a constant. So if I use I have met these three conditions, I can use the plop rule. So I go ahead then and plop in the x where I see a t. So the derivative of the integral of 1 over t squared is 1 over x squared. And so let's go look at question 2 now, and we're going to go through this checklist again. I've got the derivative of an integral. I've got the dummy variable that matches the limit variable. I've got what limit of integration that's constant. And so I can use the plop rule. So I have this expression here, t times the quantity t to the 4th minus 3. Every time I see a t, I'm going to replace it with an x. So it's going to be x times the quantity x to the 4th minus 3. For example 3 here, I'm going to go through my checklist again. I'm being asked to do the derivative of an integral, so I'm being asked to do this process that undoes the process I just did to it. I have a dummy variable that matches my limit variable. I have a constant here for the other limit, and this constant happens to be negative, and that's okay. And so I'm going to go ahead and plop the variable into this expression. So I have no idea how to do anything with cosecant in terms of differentiating or integrating, but it doesn't matter. Since I'm doing two processes that undo each other, all I'm doing is looking for the variable t in the function and plopping in an x. So the answer to this would be cosecant cubed of x. So those are 3 examples that exactly meet the criteria. And so it's literally just a straight, what I call a straight plop. Sometimes we don't exactly meet the 3 criteria, and that's the case with these 3. So for instance, if we look at this, it says let's try the plop rule now with the lower limit being x instead of the upper limit being x. I'm being asked to take the derivative of an integral. My dummy variable matches a limit of integration, but it matches the lower limit. Okay, I still have a constant for the other limit, so that criteria is met. So what I'm going to do is I'm going to re-express this using my properties of integration that we talked about in an earlier lesson, so that this variable is at the top limit. And I can do that if I want to swap these limits. Remember, I can do that by putting a minus sign out front. So now the limits are swapped, and now I've met all 3 criteria, so I can just go ahead and plop my x right in for variable t. So this ends up being minus, because of the minus sign out front, e to the x. For example 5, same thing. I have the derivative of an integral. I'm being asked to do and undo a process. I've got a dummy variable that matches the limit of integration, and I have another limit that's a constant. But again, I have these in the reverse positions. So I'm going to use my properties to reverse those and put the x at the top and the minus 4 at the bottom. And I know when I do that, that's going to put a minus sign out front of the expression. So I'm going to go ahead and plop right away with the minus sign out front. So the minus sign here is to use that property to get the x in the right location. And then I can put my x in for my t values. So I'm going to try that all with one step here again. Looking at the criteria, I'm being asked to take the derivative of an integral. I have a dummy variable that matches one of the variables in the limits of integration. The other limit is a constant. So I'm going to plop my x right in there with my t. And I'm going to put a minus sign out front so that I can acknowledge that these limits of integration have to be swapped. So the answer ends up being minus tan squared of x. So these first 3 were straight plop rules. The second 3 were kind of a modified plop, so to speak. We had to use the properties and switch our limits, and then we could just do a straight plop. And then these last 3 are situations where we go through this checklist and we're not quite meeting the criteria of the checklist, so we have to modify our approach just a little bit. So we're going to do a plop rule. And the whole idea of the plop rule is to make sure you're taking the derivative of an integral. So that's imperative. That's really important. Anything else we can kind of modify so that it works out. But in this case, we have a limit that's more complicated than just a straight x. And if you remember back to differentiation, when we had more complicated things happening inside brackets, we used the chain rule, and we're going to need it here too. So let's go through our checklist for 7. We're being asked to do the derivative of an integral. We have a dummy variable that matches a limit of integration, and we have another limit that's constant. And so we can go ahead and plop, but this dummy variable is not an exact match. It's not just an x to 3x squared. So we can go ahead and plop 3x squared in. Okay, but after we do that, we have to do a chain rule. So we can think of this as t times the quantity t squared plus 5. That's kind of like our outside function. And when we plop the 3x squared into it, that's kind of like our inside function. So we need to do a chain rule and take the derivative of our inside function. So first I'm going to plop. So I plopped my 3x squared there for t. And then I'm going to plop my 3x squared there and square it for t squared and plus 5. And then after that is done, I'm going to go ahead and take the derivative of 3x squared, which is 6x, and multiply it. So I have plop rule right here, and then times derivative of the limit, which is the chain rule. I could simplify that. This is 18x cubed on the outside. This is 9x to the 4th on the inside. So I could simplify that if I wanted to. Okay, so let's try 8. We notice that we are being asked to do the derivative of an integral, so we can use a plop rule. We just have to change up a few things. The first thing is that we have our variable in the lower limit, so we know we're going to need a minus sign out front so that we can switch those limits. The second thing is this is an x squared, so that's a differentiable function, and so we're going to have to do a chain rule. So we're going to look like minus 3. And where I see a t, I'm going to put an x squared. I'm going to plop in my variable expression, sine, and then I'm going to plop in my variable expression x squared. And then I'm going to do the derivative 2x. And so again, I've got my plop rule here, the 3x squared sine x squared. That's my plop rule. I've got the minus sign for the limit switch for that property. And I've got the 2x for the chain rule, because I have a limit of integration here that's more complicated than a straight x. I do simplify this, so it looks like I have a minus 6x cubed out front, sine x squared. So the last one, example 9, is kind of the granddaddy of them all. This is where the asterisk comes into play here. I'm being asked, if we go through this checklist again, I'm being asked to do the derivative of an integral. And I am looking at my dummy variables, and they're matching the limit of integration. But now I don't have my integration. I don't have one limit being a constant. So and that's kind of I mean, it's a very necessary thing. You might think this is a deal breaker, but we're going to use another property that you learned about integration, and that is the additive property. So we're going to pick a number between x and sine x. And and it's going to be a finite number. And the really nice thing is that it can be any number. We can decide x and sine of x are on either side of any number. So I'm going to pick 0. So I'm going to rewrite this as the derivative of the integral from x to 0 of 5 root x, or 5 root t dt, plus the derivative of the integral from 0 to sine x of 5 root t dt. So I just arbitrarily decided that x is in the middle, or excuse me, 0 is in the middle, and x is on the left, and sine x is on the right. And you can do this with, it doesn't matter the number that's here and here, because remember that number, that constant is going to be eliminated when you do the differentiating. So it doesn't matter what constant value we have in those limits. So now both of these meet this criteria, with one having a dummy variable and the other having a finite limit of integration that's constant. And this first one, we're going to need the property to put our x up top and our 0 on the bottom. So we have a minus sign in front of this one. And this one, we're going to need a chain rule, because I don't just have an x here, I have a sine x here. So with this first one, I'm going to put my minus sign out front, and I have 5 root x. I have a straight plot there because it's just a straight x. And then I have a plus. And this one is going to be, the constant is on the bottom, the variable's on the top, so that's good. So it's going to be 5 sine x. I can do a straight plot with the sine x, but now I have to do the derivative of sine, which is cosine. So that answer ends up being minus 5 root x plus 5 root sine x times cosine x. So those are some variations on the plot rule that I've seen on AP tests, and you'll see in your homework tonight. Just a quick summary. So how are the derivative and the antiderivative related? We know that the two actions undo one another. So when we're being asked to find the derivative of an antiderivative, that's a really special situation for starting and ending with the same thing. And so that's that situation where you use the plot rule. So at this point, you should be ready to do day 1 of the fundamental theorem homework.